Welcome to another video from explainingcomputers.com. This time it's my 10th annual quantum computing update. In the past 12 months, IBM and the US Department of Commerce have announced a quantum wafer foundry, Google has revealed that cryptocurrencies may become vulnerable to quantum hacking far sooner than expected, and several pioneers have reported significant progress towards the delivery of fault-tolerant quantum computers. In this video, I'm going to report notable developments from the past 12 months. And because this is my 10th annual update, I'm also going to reflect on quantum computing progress across the past decade. Before we begin, I think it's worth highlighting a few things, starting with the fact that already billions of dollars have been invested in experimental quantum computing hardware and software. And this means that regardless of how skeptical some people may be, the quantum computing industry already exists. Indeed, in June 2026, IBM alone announced plans to invest more than $10 billion in quantum computing over the next 5 years, with its CEO noting that the pace of discovery with quantum computers is accelerating rapidly. Secondly, the development of quantum computing remains a long-term research endeavour, and progress therefore needs to be judged in this context, although many now expect early practical application from around 2030. Finally, quantum computers will not replace classical computers. Rather, they are intended to augment classical hardware and to run fundamentally new computing applications. And I'll discuss what these may be later in the video. Classical computers process data using binary digits or bits that can represent a value of either 1 or 0. In contrast, quantum computers use quantum bits or qubits. Due to a quantum phenomenon called superposition, qubits can exist in more than one state at exactly the same point in time. And this allows them to process far more computational states simultaneously than classical bits. Pairs of qubits can also become entangled, which means that the state of one qubit is tied to the state of another regardless of the distance between them. 10 years ago, the focus in quantum computing was on increasing the number of physical qubits in a quantum processor, and this allowed the development of so-called noisy intermediate scale quantum or NISQ hardware. But because physical qubits are highly prone to error, more recently a lot of research has been directed into quantum error correction or QEC in pursuit of fault-tolerant quantum computing or FTQC. And this has led to a revised focus on logical qubits. A logical qubit entangles many physical qubits into one error-corrected one. As detailed in last year's update, in December 2024, Google introduced Willow, the first quantum processor where error-corrected logical qubits get exponentially better the more physical qubits are used to make them. And, as Harman Neven, founder and lead at Google Quantum AI explained, this was a strong sign that useful, very large quantum computers can indeed be built. IBM is also developing hardware where a large number of physical qubits will be combined into a smaller number of logical ones. By 2029, IBM plans to deliver a fully fault-tolerant quantum processor called Starling with 200 logical qubits. And IBM has a strong track record of meeting its quantum computing goals. Both IBM and Google's quantum processors are based on superconducting qubits. These are comprised of a pair of metal strips that become superconducting when cooled to almost absolute zero. However, over the past 10 years, other qubit technologies, known as modalities, have also been brought closer to practical application, as I've detailed in previous updates. For example, Intel has developed silicon spin qubits that can be manufactured using its existing fabrication techniques. Meanwhile, PsiQuantum and Xanadu have developed photonic qubits that are created using ring resonators to squeeze laser light. In February 2025, PsiQuantum announced a quantum photonic chipset called Omega that can be created using traditional lithography. And in June 2026, it broke ground at a site in Australia where it plans to build a utility-scale, or in other words, practically useful, fault-tolerant photonic quantum computer. Also showing great promise are neutral atom qubits, which are made from individual atoms that are manipulated in a vacuum by lasers. Pioneers include Atom Computing and QEra, with Google also recently announcing its intention to develop the technology. In June 2026, Atom Computing announced that it had demonstrated quantum error correction, with error rates declining as more physical qubits were used to make logical qubits. And this was a first for neutral atom hardware. Meanwhile, fellow neutral atom pioneer QEra has plans to launch a fault-tolerant system called Libra in 2028. This will have 256 logical qubits based on over 10,000 physical qubits and is expected to be followed by a 1,000 logical qubit system by 2029. Also showing great potential are trapped ion qubits. These are formed from ions that are held in place in a vacuum by electromagnetic fields and manipulated by lasers. Significant pioneers include IonQ as well as Quantum, who in June 2025 reported demonstrations of repeatable error correction, which they believe will allow them to deliver a fully fault-tolerant quantum computer by 2029. Lastly on our table, since 2022, Microsoft have reported success developing topological qubits. These are based on a topological phase of matter that's not a solid, liquid, or gas, and which Microsoft claims to have created using particles called Majorana zero modes. In June 2026, Microsoft revealed Majorana 2, its second topological qubit processor. Microsoft also reported that this has qubits which can maintain their quantum state 1,000 times longer than the first generation Majorana 1 processor announced just 16 months earlier. And given progress to date, Microsoft believes it will deliver a scalable, commercial, topological quantum computer by 2029. This said, not all quantum scientists are convinced by what Microsoft has claimed. And, talking of controversy, I feel compelled to mention D-Wave Systems. In 2011, D-Wave sold the world's first commercial quantum computer. However, D-Wave hardware is based on quantum annealing, and this is contentious because it's not a gate-based qubit technology over which users have total control. In January 2026, D-Wave acquired Quantum Circuits, a company that develops superconducting gate-based qubits. And in June 2026, D-Wave issued this press release about charting a new course to fault-tolerant quantum computing with a gate model roadmap. In my first quantum computing update, I reported how, on May 4th, 2016, IBM made an experimental quantum computer publicly available over the internet. And since this milestone, many other pioneers have put quantum computers in the cloud. These have included D-Wave Systems, who launched a service called Leap in 2018, Amazon, who announced Amazon Braket on AWS in 2019, and Xanadu, who launched their photonic cloud computing platform in 2020. Today, Quantum as a Service, or QaaS, remains a research tool. But it's also likely that the first commercial fault-tolerant quantum computers will be accessed from the cloud. Here I've listed 9 QaaS pioneers. All provide access to real quantum hardware, not just simulators, and include the big 3 classical cloud computing providers, industry giant IBM, and 5 quantum computing pure plays. As an aside, I find it interesting that all of these are now public companies, following the IPOs for Xanadu in March 2026 and Quantum in June 2026. Back with our table, it's worth noting that Amazon and Microsoft are already operating as Quantum-as-a-Service brokers as they facilitate access to hardware from other pioneers. Specifically, the Amazon Bracket service on AWS provides access to quantum computers from AQT, IonQ, IQM, QEra, and Rigetti. Meanwhile, Microsoft's Azure Quantum provides access to hardware from IonQ, Pascal, Rigetti, and Quantinium. It should be noted that the Google Quantum Computing Service also provides access to hardware from a range of providers. However, this is currently only granted to those on an approved list with no general public access. Finally, it's worth noting that many cloud quantum providers offer free open source software frameworks, simulators, and related learning resources. So, if you want to develop quantum computing skills, you can, for example, check out free access to IBM's Qiskit, the Microsoft Quantum Developer Kit, and Google's Cirq. So, what will future quantum computers be used for? Well, molecular modelling and simulation, also known as quantum chemistry, is currently expected to be the flagship application. IBM first simulated a molecule back in 2017. And Microsoft now heavily associates quantum computing with accelerating scientific discovery. To this end, in 2023, it launched Azure Quantum Elements, an HPC and AI system to accelerate chemical and materials science, and which includes tools that will help scientists prepare for a future where a scaled quantum computer could accurately model the most complex molecule. Today, classical supercomputers are unable to simulate the molecular activity in a cup of coffee. Granted, we have software, such as the MolView package we're running here, that allows us to build molecular models. And some existing packages can simulate the basic chemistry of how molecules behave. Nevertheless, none can accurately simulate the quantum mechanical systems of subatomic particles inside an atom. Back in 1981, physicist Richard P. Feynman published this famous paper, and in it he concluded that natural quantum mechanical systems can only be simulated by a quantum computer. This is because a quantum system is required to simulate a quantum system. And 45 years later, the race is on to make this happen. IBM, for example, has a focus on quantum-centric supercomputing, which will integrate quantum coprocessors with classical HPC systems to help simulate the natural world. Using quantum computers to perform molecular modeling and simulation will improve our understanding of chemistry, physics, and biology. And, in turn, it should deliver improvements in materials science, engineering, and healthcare. This March 2026 paper from the OECD indeed notes that potential commercial applications span a range of business sectors, including pharmaceuticals, advanced materials, energy, finance, and transportation. The first two of these stem directly from an ability to simulate the natural world, whilst molecular modelling will also help the energy sector to improve batteries. In addition, future quantum computers may optimize the operation of power grids. Indeed, after molecular simulation, the second most anticipated quantum application is running complex optimizations, with applications also expected in the financial sector as well as in logistics and transportation. In addition to improving our understanding of physical reality, future quantum computers will be able to break a lot of existing digital encryption. In March 2026, Google published this blog on quantum vulnerabilities, followed by this white paper about the need to upgrade cryptocurrency encryption. The key message is that 20 times fewer qubits will be needed to break 256-bit elliptic curve encryption than previously thought. And this is why Google has set a timeline of 2029 for migrating to post-quantum cryptography, or PQC. Over the past 5 years, quantum-resistant cryptographic algorithms have started to be developed. And across the next 5, I'm certain that we'll see significant efforts to encourage a mass migration to post-quantum cryptography. This said, whilst governments and their militaries will invest in quantum computers as code-breaking weapons, few companies are likely to purchase quantum computing resources to engage in illegal activity. However, with a looming threat of quantum cyber attacks, most businesses will need to improve the security of their classical computer systems. In this video, I've tried to provide a non-technical overview of some key quantum computing developments. Compared to 10 years ago, the field is now too large for everything to be included. And I also know that regardless of what I say, some people will never believe that a quantum computer exists. And yet, according to this 2026 Quantum Economic Development Consortium report, the quantum computing industry generated annual revenues of $1.4 billion in 2025, with these projected to grow to more than $3 billion by 2028. In April 2026, McKinsey even predicted that quantum computing could deliver $1.3 to $2.7 trillion in economic value to companies worldwide by 2035. Certainly, this is just a prediction, but I do now think there is a strong probability that fault-tolerant quantum computers will be running new kinds of computing applications in the 2030s. But now that's it for another video. If you've enjoyed what you've seen here, please press that like button. If you haven't subscribed, please subscribe, and I hope to talk to you again very soon.